Hey everyone, welcome back to the series, where we're building a neural network from scratch in C++ for robot collision prediction. If you haven't seen the introduction video yet, go check it out so you understand exactly what we're building in this series. In this video, we're going to finish our Layer.hpp file by creating the layer struct, the part that represents a single layer in our neural network. Let's jump right in. We start by defining the layer struct. Struct layer. This will represent a single layer in our neural network. It holds important data like activations, biases, and gradients, as well as functions to apply the activation. Let's break it down step by step. First, we have two private member variables. So we say private activation function, activation, and activation function, activation underscore derivative. These will store the activation function and its derivative for the layer, depending on what we choose, ReLU, sigmoid, or not. Next, we have the public members of the struct. Public, and here's the first one, int layer underscore index. It stores the position of this layer in the network. And next we have int size. Stores how many neurons are in this layer. Next we have a vector of double, std vector double, and we're gonna call it z. This vector stores the pre-activation values, what we get before applying the activation function. And we have another vector, std vector double a. This one stores the activation output values, the results after we apply the activation function. And next, std vector double bias. The bias vector stores the bias values for each neuron. A bias helps adjust the output of a neuron independently of the input by shifting the activation output. This gives the model more flexibility to fit the data and learn better patterns. Next we have std vector double gradient. And the gradient vector stores how much each neuron contributes to the error, the difference between the actual value and the predicted value. We use these gradients during training to update the weights and biases and improve the model. Now let's move on to the constructor. Here's how we set up a new layer. Layer, we take the layer's index, its size, and the activation type. Int index, comma, int size, comma, activation type, act underscore type. We assign the index parameter to the layer underscore index variable in the struct. Layer underscore index, inside parentheses, index. And the size parameter to the size variable, size, inside parentheses, size. Then we initialize the z and a vectors to hold the layer's data, and we fill them with zeros so they're ready for computations. And here we say, comma, z, size, comma, 0.0, and a, inside parentheses, size, comma, 0.0. Let's also check if the size is valid. We don't want layers with zeros or negative neurons. If size less than equals 0. And here we throw an exception. Throw std invalid underscore argument, and we pass it this message. Layer sizes must be positive. Now we add a condition here, because we only add bias for non-input layers. The input layer does not have biases. So we say if index is not equal to 0, This checks the current layer is not the input layer. If it's not, we initialize the gradient vector and the bias vector, both filled with zeros. Gradient equals std vector double inside parentheses size comma 0.0, and bias equals std vector double inside parentheses size comma 0.0. Then we assign the activation function and its derivative by calling getActivationPair with the activation type we passed into the constructor. The first element of the pair is the activation function itself, and the second is the derivative. So we say activation equals getActivationPair, and we pass it act underscore type dot first, and activation underscore derivative equals getActivationPair, and we pass it act underscore type dot second. This setup ensures that each non-input layer has the correct activation function, its derivative, and properly initialized biases and gradients ready for training. Next, let's create a method to apply activation function to a single value. We'll call it apply activation, and it takes a double as input. Double apply activation, and it takes double x, and here we use const, which means this method does not modify the state of the object it belongs to. Inside the method, first we add a safety check. If this layer doesn't have an activation function assigned, maybe because it's the input layer or there's an error, we throw an exception. If not activation, throw std runtime underscore error, we pass this message. This layer has no activation function. Otherwise, we just call the stored activation function on X and return the result. Return activation, and we pass it X. This method will be useful later when we pass data through the network during forward propagation. Now let's add a method to apply the derivative of the activation function. This is important for back propagation. We'll call it apply activation derivative, and it also takes a double as input. Double apply activation derivative, and it takes double x const, and just like before, we add a safety check. If this layer doesn't have an activation derivative assigned, we throw an exception. If not activation underscore derivative, we throw std runtime underscore error, and we pass it this message. This layer has no activation derivative. Otherwise, we simply call the stored activation derivative function on X and return the result. Return activation underscore derivative, and we pass it X. At the end, we have two optional helper methods. And here's the first one. Bool has activation const, and we return static underscore cast bool, and inside parentheses activation. Static underscore cast bool activation explicitly checks whether the activation function is assigned by converting the function object std function to a boolean. It's true if it holds a valid function, false if it's empty. And then we have bool has derivative const, and it will return static underscore cost bool, and inside parentheses activation underscore derivative. These methods just check whether an activation function or its derivative is set for the layer. Well, we're not using them in this project right now, but it's a good idea to keep them around. They might come in handy in a future series, or if we expand the project later. And that's it. We have finished the Layer.hpp file. We now have a solid structure for each layer in our network, including activation functions, biases, gradients, and the data we'll use for forward and backward passes. In the next video, we're going to shift gears and work on the matrix class. We'll use it to handle all the matrix operation that our neural network needs. If you are enjoying the series, don't forget to like, subscribe, and hit the bell so you don't miss what's next. Thanks for watching, and I'll see you in the next video.